Okay, second part of the refraction video. Now, did you find, first of all, sine I divided by sine R when you're going from here, from air into your glass? You should have found the fact the ratio was about 1.5-ish. And then if you did this one, which is now going from glass going to air, did you now find it's about 0.6-ish? And then did you suddenly realize if you then take 1 divided by 0.5, you get about 0.6. In other words, they're inverse related. Yeah, of course you did. So with that then, the guy who did the work on this was Snell. And like all these famous physicists, he wanted you to remember more, and he wanted to find a law, and he called it Snell's law. So he realized the fact that there must be a relationship between the angle of incidence and the angle of refraction. He tried those things, and eventually went to symmetry. And then he eventually realized, by playing around with the mathematics, etc., if he did sine I divided by sine R, he got a constant value. He then said that constant was n. And what n stands for is the refractive index. Okay, and if you go glass to air, air to glass, mentioned before, here is when we're going glass to air, we find it 1.5, we find it 0.6. Therefore, this one is 1 over n compared to that one there. It doesn't make sense then, with all of these, that the fact that the refractive index is dependent on material. So going back to here, and you can see it here, and here you've got the refractive index for water is 1.33. And I've realized I've not checked. I did that water, not glass. Apologies. I left it last time. I made that glass. And when you had glass going to air, it's 1.5. If you then change to water, for example, it comes up to 1.3, and therefore different materials have different refractive index. That makes sense because if you look at the wave idea, the waves going through is the waves slow down by a varying amount. In other words, the speed here compared to the speed there, the ratio changes, and you can actually look at the refractive index from the speed of the water waves or the light going from that medium going to this medium. It works exactly the same. So going back to here, this is what you found, and this is called Snell's law. And Snell's law simply states that refractive index of material, going from glass to air, whatever it is going to ratio of the sine I divided by sine R. So you will find these then on page 189, question 2, and eventually I'd like to do all the summary questions on page 189, show you how you lay them out, because I know you're fantastic in laying these out. Is I would like you to do this way. You do n is equal to sine I divided by sine R, and you're going to show all your working. So case here, the first one, your refractive index is going to be 1.5, and therefore this, I've got the angle of incidence is equal to 30 degrees. Now what you do then is you want to find the refractive index. So you can rearrange your equation. Sine R then is equal to sine I divided by n, which is going to be sine 30 degrees divided by 1.5. And we all know we put in the calculator sine 30 is 0.5, and you then divide it by 1.5. Now, when you do that, you then will get the sine, oh dear, I lost my pen now. That is going to be the sine R. So you have to go into your calculator and do the inverse of the sine to the minus 1 of that number. And when you do that, then you'll find the angle of, did the wrong one, did I rather than R. You find then the angle R, I think it pops about 19.5 degrees. In some respects, you should round that up to 20 degrees. I'd like you to have a go at all the other questions just here. But basically, I want you to do all the summary questions 1 all the way through to 4. Now, the little bit also in your books, it mentions about the prism. To show you the prism, which is an interesting device, is going back to my simulation over here. Ooh, no, didn't want that one. Try again over here. I think I can go home, and here's going to be a prism. Yeah, here it is. So I'm going to put a prism in here. Now, again, we can do this experiment in the lab. We can take the laser, and what we can do is shine the laser like this into the position where I want to. And the light ray comes along here, and here you can see, first of all, it's going to bend towards the normal. It's going from air to glass, and here is going to bend away. But because the sides are not perpendicular, sorry, try again, the sides are not parallel, they're at an angle, it means then the ray of light comes out at a different angle than it went in. In other words, what we find here is we have something called deviation. Now, the other thing I'll show you now, because it comes up later on, see the red light here? If I suddenly then change the light to a different color or a different wavelength, and here you've got the wavelength in nanometers, can you notice again, there's a slight change in the angle, and move it quickly, is more visible. And we're going to look at an equation later on where you can actually see, let's see, put the normals on, I want to notice that. When you can look at the angles going through here, the deviation happens, but the actual amount of deviation is dependent on wavelength, because the amount of refraction is also dependent on the wavelength, and that will come up in an equation to do later on. So what I'd like you to do is I'd like you to have a go at those calculations going from there. So what I've been through in these two little videos is I've now explained to you the principle of refraction, and you state Snell's law, and now you're starting to do the form calculations using Snell's law. Hope you enjoyed the video.